Good morning, one and all. Today we start a new chapter, feedback amplifier. Previously we have learned voltage amplifiers, their frequency response, and multi-stage amplifiers. In the voltage amplifiers, we have carried out the analysis of amplifiers by considering voltage gain, current gain, input impedance, output impedance, and so on. In the frequency response, we have obtained the bandwidth of the system, bandwidth of amplifiers. Whereas in case of a multi-stage amplifiers, the gain of the system is improved by considering the number cascading the number of individual stages. From these three chapters, it is seen that the analysis of any amplifier or performance of any amplifier is checked by number of parameters like voltage gain, input impedance, output impedance, bandwidth, etc. So all these parameters need to be controlled. And this controlling can be done by with the help of a feedback. So that's why we need to understand what is meant by the feedback and what are the feedback amplifiers. Firstly, what is meant by the feedback? When a part or a fraction of output is combined to the input, it is called as a feedback. Thus, the process of combining a fraction of output energy may be voltage or current, back to the input is called as a feedback. When feedback voltage or a current is so applied as to increase the input signal, that is, when the feedback is in phase with the input, is called as positive feedback. Also called as direct feedback or regenerative feedback. With a positive feedback, system have a excessive distortion and instability. These features are used for in case of oscillators. So the oscillators basically are positive feedbacks. When the feedback voltage or a current is so applied to with the input signal, that is, when the feedback is out of a phase to the input, is called as negative feedback. Also called as inverse or degenerative feedback. With negative feedback, the gain of the system reduces. This is a disadvantage. But with this disadvantage, it has a number of advantages. It improves bandwidth of the system, improve stability of the system, gain stability, improve the non-linear behavior of the system, decreases noise of the system, decreases output of the system, increases input of the system. So these are the number of advantages with a negative feedback. Disadvantage, gain increase. This reduction in a gain can be compensated by considering a number of considering cascading of a number of integer stages. So the gain is infinite. Let's now we will concentrate on what is the basic principle of feedback amplifier. Let's firstly we have to define the number of parameters firstly. So this one is the first basic amplifier. Some part or a fraction of output is taken from the basic amplifier and is given to the input of the basic amplifier. So this is a feedback network. This feedback network is having its input as well as output. Also for a basic amplifier, it's having a input label as a V, output label as a Vout, and to this one at output port we have connected here a load RL. The basic for the feedback amplifier, input to the feedback amplifier is a output of the basic amplifier, fraction of a basic amplifier, output of the fraction of a basic amplifier, and the output of this feedback amplifier label as a VF. So the gain of the feedback network is given as output entity to the input entity. Output entity we are labeled as a VF, input entity we are labeled as a Vout. So the gain of this one is VF divided by Vout with the feedback factor K. The output of the feedback network labeled as a VF, which is given as the product of these two terms, the gain of the feedback network and the output, so which is a K times V out. So let's now, this is the external source, so sorry, function generator signal Vs is applied. If the switch S is open, then this feedback network is not coming in picture. That time the gain of this basic amplifier is given as the output of the basic amplifier and input to the basic amplifier. So for this situation, S1 is open, input to the basic amplifier is simply a Vin. So finally output of the gain, finally the gain of the system is given as Vout divided by Vin. So which is called as the gain of the basic amplifier. But it's also called as the gain of the system without feedback, which is called as labeled as AV is equal to Vout divided by VA. Let's now S1 switch is closed. As switch is closed, the fraction of output of a basic amplifier is given to the feedback network. So the output of the feedback network is given as the gain of the feedback network and input available at the feedback network, which is a Vout. So finally output available at the feedback network is K times Vout. So thus input available at the basic amplifier is not a simply Vin, it is a modified input. We will label this one as a Vin dash, which is given as Vin output of the which is given as input of the basic amplifier and output of the feedback network, which is a Vin plus K times Vout. So at that time, if the feedback network is coming in the picture, since switch S1 is closed, the output of that is labeled as a Vout dash. And if you want to find out the gain of the system by considering the feedback, which is given as Vout dash divided by Vs, we will label as this one is a voltage gain with feedback. So this analysis, let AV is equal to Vout divided by V, the voltage gain without feedback, and if with the feedback, new input is a Vin dash, which is a input of the basic amplifier and output of the feedback network K times Vout. So the output, new output is a Vout dash is equal to gain of the basic amplifier and modified input Vin plus K Vout. So the finally rearranging this equation, we will have Vout dash divided by Vin is equal to AV divided by 1 minus KAV, where AV is the voltage gain without feedback. The K is the gain of the feedback network. The product K into AV is called as loop gain. This is a basic expression for a feedback amplifier. Finally, we have the voltage gain with feedback. AVF is equal to AV divided by 1 minus KAV. This K is a feedback network gain. So this K will be decided what are the different types of feedback. So the K may be greater than 0, may be less than 0. So the K, or there are two types of feedback, the positive feedback as well as a negative feedback. If we consider the negative feedback, this K will be replaced by negative value. So finally, the expression for a negative feedback is become as AVF is equal to AV divided by 1 minus of a minus KAV. Finally, AV divided by 1 plus KAV. Whereas for the positive feedback, this K is a greater than 0, it's a non-zero. Greater than 0. So this K will be replaced by simply a positive K. So finally, for positive feedback, expression remains as it is. So thus by clubbing this positive and the negative feedback, this AVF can be written as AV divided by 1 minus plus KAV. Minus plus KAV. So where a positive as well as a negative feedback is there. So if we consider that the negative feedback, for a negative feedback expression is AV divided by 1 minus KAV. AV divided by 1 minus KAV. Let's say if we consider that, for example, AV is voltage gain without feedback is a 40 and the feedback factor is a 10% negative feedback. So if we simply plug these, so the voltage gain with feedback, which is given as AV divided by 1 minus KAV, but K is a negative, so it's by plugging this value 10%, we will have the voltage gain is 8. So with the negative feedback, the gain is reduced. So if for this case, we have the gain in the reduction is almost 80% by finding 40 minus 80 divided by 40 into 100%, 80%. So finally we can say with the negative feedback, the voltage gain reduces. What about the for a positive feedback? For a positive feedback, the basic expression we have the AV is equal to AV divided by 1 minus KAV. So let's see if we consider that AV is equal to 40 and the feedback is 1% positive. So by plugging that value, so you have the voltage gain with feedback is 66.66, approximately 67%, 67. The voltage gain without feedback is 40 and voltage gain with feedback is 67. So thus with the positive feedback, the gain is improved. But with the negative feedback, gain is reduced. So still, as the gain here, voltage gain is increased in case of a positive feedback, and in case of a negative feedback, gain is a decrease. In the most of the applications, negative feedback is preferred because there are a number of advantages. The first advantage is that first one is improve its stability. So what is meant by the stability? We know that the voltage gain with feedback for negative feedback is given as AV divided by 1 minus of a minus KAV. Finally, AV divided by 1 plus KAV for a negative feedback. So definitely 1 plus KAV, this term, so KAV is more than this one. So finally this one can be a 1 plus KAV approximately written as a KAV. So finally AV divided by KAV is equal to 1 upon K. So finally it is seen that for the negative feedback, with a negative feedback, voltage gain is depends on the only feedback factor K. It not depends on the gain of the basic amplifier or the parameters associated with the basic amplifiers, or it's not depends on the what is the beta of the transistor. It's simply depends on what is the gain of the feedback network. So thus the stability of the system only decide the what kind of a feedback, what is the gain of the feedback network. The second, the what is a bandwidth. So here bandwidth is improved. Let's say if we consider that the frequency response of a typical frequency response of a RC coupled amplifier without feedback is like this way, where you will have the lower cutoff frequency, upper cutoff frequency. From this one we have found out it's a bandwidth, which is given as label as a BW, is given as a F2 minus F1. And like we want to find out what should be the bandwidth with feedback that we need to find. So this bandwidth with feedback is labeled as BWF is equal to F2 dash minus F1, and which is given as bandwidth of a base without amplifier into 1 plus K times AV. So we need to find out this expression, and for that purpose we use focus on their deviation, and for that we will consider on a frequency response chapter, where we know what is the relation between voltage gain at a mid frequency and low frequency, and the voltage gain at a mid frequency and the high frequency. So we know that the voltage gain at low frequency is given as AV mid divided by 1 minus J times F1 divided by F, where F is the applied frequency, F1 is the lower cutoff frequency. When the negative feedback is applied, what will happen? So let's AV at a mid frequency is given by AV mid divided by 1 plus KAV mid from basic expression of a voltage gain, basic expression of a feedback amplifier, which is a AVF is equal to AV divided by 1 plus KAV. So similarly we will have AVF at a low frequency given as AV low F is equal to AV low divided by 1 plus KAV. Now we want to find out what is the bandwidth for feedback network. So let's firstly we'll consider low frequency, voltage gain at low frequency and voltage gain at low frequency by considering these two factors. So plugging this value in this expression, we are plugging this value. So finally we will have the AVF at a low frequency is given as AV at mid frequency is divided by 1 minus J times F1 divided by F divided by 1 plus KAV mid divided by 1 minus J F1 divided by F. So if we slightly rearrange this one, so finally we will have this expression as AV mid divided by 1 minus J F1 divided by F plus K times AV mid. So we will take it 1 plus KAV mid as a common from a denominator and adjust it to the numerator. So finally AV mid divided by 1 plus KAV mid divided by 1 minus J times this term. And we know that AV at a mid divided by 1 plus KAV at a mid is a voltage gain with feedback, which is AVF with feedback. And let we will define one parameter as F1 dash, which is a 1 upon F1 divided by 1 plus KAV mid. So this is F1. Similarly, if we go for at a high frequency, AV at a high, which is given as AV mid divided by 1 plus J F2 divided by F1. When negative feedback is applied, if we plug all these expressions, finally you will have this again expression, which is a AV mid divided by 1 plus KAV mid divided by 1 plus J times F divided by F2 into 1 plus KAV mid. So finally we will have the AV. Finally, it is seen that AV is equal to AV mid F divided by 1 plus J times F divided by F2 dash, where F2 dash is upper 3 dB frequency of a amplifier with a feedback, which is given as F2 times 1 plus KAV mid. where F2 is upper 3 dB frequency of a basic amplifier. Now the bandwidth of a feedback network is a bandwidth of a feedback with feedback is given as BWF, written as F2 dash minus F1 dash. By plugging the value of F2 dash and F1 dash, we have F2 times 1 plus KAV minus F1 divided by 1 plus KAV. From graph, it is seen that bandwidth without feedback is given as BW and with feedback is given as a BWF. This is the difference between upper 3 dB and the lower 3 dB. So BWF is equal to F2 minus F1. BW is equal to F2 minus F1 and BWF is equal to F2 dash minus F1 dash. From this expression, it is seen that F1 is small as compared with F2. So finally, this bandwidth expression can be written as approximately F2 minus F1 as a F2. And similarly, for bandwidth with feedback, BWF is equal to F2 minus F2 dash minus F1 dash, where F1 dash is very small as compared with F2 dash. Similarly, we can write BWF is equal to F2 dash. So, if we concentrate on this expression by considering the graph consideration, so BWF is equal to, finally we will have the F2 dash, but F2 dash is a F2 minus F2 times 1 plus KAV mid. So finally we will have the F2 times 1 plus KAV mid, but F2 is approximately a bandwidth without feedback BW. So thus the bandwidth with feedback depends on the factor 1 plus KAV, which is increases the bandwidth of the basic amplifier by the feedback factor 1 plus KAV. Next important parameters, distortion. Distortion is a decrease with the negative feedback. How that? What is meant by the distortion? If the distortion is present in the system, means it's that output is not exactly replica of the input. And this is because that it may be there present in spite of a fundamental harmonics, there are second harmonics are present, and due to that there will be signal amplitude will be a distorted, and this signal amplitude we want to minimize it. So for feedback amplifier, the distortion for feedback amplifier distortion is given as a D subscript F. Let D will be a distortion of a basic amplifier, and it is given as by DF is equal to D divided by 1 plus KAV. If we consider that distortion is a 10% and the AV is a 40, distortion is a 10, AV is a 40, and the feedback is a 1%. For that case, you will have the distortion will be reduced from 10 to 7.14. So we want to reduce the distortion in the primary interest, and the gain is a cheap. Then how to get the idea about this one? So let's see if we consider that this is a input sine wave we have applied, okay, for the basic amplifier, means for without a feedback amplifier, and the output of the system we will have like this way, which is amplified. And let's say we same the input we will apply here the sine input as a VI is applied to the feedback amplifier, and the output of the response is getting like this way. Definitely for the feedback amplifier the gain of the system is reduced, so definitely output is also reduced, no issue about that. If you concentrate for the interval O to A, 0 to A interval, as the input is a sine wave, output is also amplified. Similarly for the same case for the with the feedback also there, but for interval A to B, for interval A to B, as the input is having a notch is there, that is also amplified in the with in the basic amplifier, which is create a deep deep is there. But whereas for the without a feedback, for the there as here it is a notch is there, this amplifier there is has a less deep. So from this it is seen that with the negative feedback, their output is also tries to get as exactly replica of a input, exact replica of a input. Let's now we will go for the fourth parameters, which will decreases the noise. So the noise for the feedback amplifier is given by label as the NF, and the noise of the basic amplifier N, and it is given as by considering that NF is equal to given as NF N divided by 1 plus KAV. Since here is a feedback factor, since this noise is divided by 1 plus K times AV factor, so definitely noise factor is improved. Next, the input impedance. Now, before starting this one, we have to go for what are different types of negative feedback configurations or connections. Feedback may also be classified as a voltage feedback and a current feedback. In the voltage feedback, the energy feedback to the input terminal is proportional to the output voltage, while in the current feedback, the energy feedback to the input terminal is proportional current through a load. Both this voltage and the current may be fed back to the input either in a series or a parallel shunt, resulting in there are four basic feedback connections. First one, voltage series feedback, where voltage is taken from the output part parallel, and it is given to the input in a series, so it's a voltage series feedback. Next, voltage shunt feedback, where output is taken and it is connected parallel to the input, and here input to the basic amplifier is a source current, whereas for this case input to the basic amplifier is a voltage source. Next classification types, the current series feedback. For a current series, we want to take a current from the output, so we have to tap the current, and we are taking the current in a tapping form, and it is given in series with the input. Given in a series with the input. Again here, input to the basic amplifier is now voltage source. Whereas for the last configuration, current shunt feedback network, we want again the current from the output, we will tap it, and that is taken and it is connected parallel to the input. And for this case, we will have the input to the basic amplifier is a current source. So if you observe that from these three, all these configuration, for a series configurations, for a series feedback, input to the basic amplifier is a voltage source, since for a series voltage get distributed, whereas for a shunt configuration, input to the basic amplifier is a current source, since for shunt configuration, for a parallel configuration, current gets divided. So this is the more important, so that for a voltage series feedback, the gain of the basic amplifier is a Vout divided by Vin, and the feedback network is a K or a beta Vf divided by Vout. For a voltage shunt, the voltage gain is AV is nothing but output to the input is Is and the In, and the feedback network is a gain is a Vout, and output is a IF is there. For similarly, if you go for the current series feedback, so the input is a V in and the output is a current, so its a gain is a I out divided by V in, and feedback network gain is input is I out and the output is a VF, so it's a VF divided by R. Finally, for a current shunt feedback, input is a I and output is a I out, so output current to the input current, and the gain of the feedback network may be a beta or a K. Input to the feedback network is a I out, output of the feedback network labeled as a IF, so finally gain is IF divided by I out. Coming back to the feedback parameters, which one we have left is the input resistance, input impedance increases. So let's firstly we will go for the series feedback configurations. So for a series, we know that the voltage is the input, and for a series feedback, let's say gain of the basic amplifier is represented as this one, and the gain of the feedback network block is represented as this. So the gain of the basic amplifier is having its input impedance, output impedance, and the gain of the basic amplifier AV is applied input voltage, and the gain of the feedback network is output voltage of a feedback network to the input voltage of a feedback network, which are labeled as a KV out and V out respectively. So finally gain is given as a VF divided by V out. So let's say input impedance seen at the input side of the basic amplifier is Rin without feedback. If we consider the feedback, we will label the input impedance seen at this one is Rin-F. Similarly, we will go for the output impedance seen at the basic amplifier without feedback is RO, and with feedback ROF. So we want to investigate what is a input impedance expression for a series feedback connections. From the block diagram, it is seen that input current IN is nothing but a drop available at this point and resistance offered by this one. So Vin divided by Rin is the input. But what is a Vin? Vin is nothing but a voltage available at this point, which is nothing but a source voltage, and this one output of the feedback network Vf. So if we trace this loop, this total loop, so we will have Vin can be replaced as Vs minus Vf. So finally we will have Vs minus Vf, but Vf is the output of the feedback network, which is given as the KV out. By plugging this one, we will have the expression Vs minus K times V out. So but V out is what? The V out is the output of the basic amplifier, which is given as the gain of the basic amplifier into the input of that one. So which is given as V out is replaced by AV divided by V8. So finally, if we slightly rearrange this expression, we will have input current into the input resistance without feedback is equal to Vs minus K times AVV. Slightly rearrange these expressions. Finally, we will have the Vs is equal to Vs is equal to In times Rin plus K times AV Rin. By taking Rin as a common, finally we will have Rin times 1 plus K AV. So finally we will have Vs divided by Rin. But what is a Vs divided by Rin? Vs divided by Rin is nothing but input impedance measured at the basic amplifier considering the feedback network. So which is labeled as V-in-F. So we will write this one as a V-in-F is equal to Rin into 1 plus K times AV. From this expression it is seen that the gain of the basic amplifier, input impedance of a basic amplifier is Rin, and with feedback the input impedance is changed to 1 plus K times AV. So it's a simply multiplication. So it's a seen that for a series connections the input impedance is improved. What about for a shunt feedback? For a shunt feedback, we know that input source is a current source. So we consider that the input impedance of a basic amplifier is Rin. The gain of this one is A into Rin, input of this one, and which is output impedance Ro. Output voltage without feedback is Vout. Okay, and we are interested for the input impedance, so we will consider input impedance with feedback. So with feedback we will label as R in F. So for this investigations we want to find out what will be the uh, input impedance for a shunt feedback network. So from the feedback network connection, it is seen that this source current is distributed into two parts. By the KCL law, we will have it's a IN plus IF, but IF is nothing but output of the feedback network, which is a K times V out. So finally, we will have the IS is equal to IN plus IF, but so by plugging the value of IF, we will have the K times V out. Okay, so we will have, now we will consider, we are interested for what is the input impedance seen at this point. Input impedance seen at this point is a drop across this one and current drawn from this one. So the input impedance seen at this point is a drop across this, which is the input voltage, and the current drawn from this one is the IS. So we will have the input impedance with the feedback Vin divided by IS is equal to Vin divided by I. By plugging the value of IS, In plus IF. So finally we will have Vin divided by In plus K times V out. So we will take it In as a common, and finally you will have Vin divided by In divided by 1 plus Ka V out divided by In. So Vn divided by In is nothing but input impedance of input voltage of a basic amplifier to the input current, which is the input impedance, and V out divided by In is the gain of the basic amplifier. So finally we will have the input impedance with feedback for shunt connection is given as Rin divided by 1 plus KAV. So thus the input impedance for either voltage or current series feedback is decreased by factor 1 plus KAV. So previous analysis for a series, it's a increase by 1 plus KAV, and for a shunt it is a decrease by 1 plus K. For a shunt analysis, it is seen that it is a decrease by factor 1 plus KAV. Rin F is equal to Rin divided by 1 plus KAV. Now next we will go for the output impedance. With the negative feedback, output impedance is a decrease. How? That we have to consider by considering a number of configurations. Let's firstly we will go for voltage series configuration. Referring to the output series, referring to voltage series configuration. For this configuration, we want to find out output impedance, and for this purpose, we will trace this loop where it is you will have the output voltage in a series with this configuration. So if we apply the Kirchhoff's voltage law to this loop, we will have the V out is equal to Ro into I out plus AV divided by V. And from this expression, which can be written as like this way, V out is equal to V I out into Ro plus AV into V in. But V in is nothing but feedback voltage, and the feedback voltage is given as K times V out. So finally, from this expression, we will have the slightly rearrangement of this expression. V out divided by I out is equal to, which is given as output output impedance with the feedback label as ROF is equal to RO divided by 1 plus KAV. From this expression, it is seen that output impedance for voltage series feedback, it is decreased by factor 1 plus KAV. Similarly, if we go for the current shunt feedback analysis and current series feedback analysis, it is given that RO times 1 plus KAI, and for current series feedback, RO times 1 plus KAI. So from this one, it is seen that for voltage series feedback and Now we want to summarize all these factors as give the comparison amongst them. It is given as that for voltage series, voltage and the current series as this, the voltage gains decreases for all the configurations, stability increases for all configurations, distortion, noise, bandwidth, all these are the remains for all constant for all the configuration. Only change is that input impedance and output impedance. So whereas for voltage series, for series configuration, input impedance is given as the Rin times 1 plus Ka, for whereas for shunt configuration it is given as Rin divided by 1 plus Ka. So it is a decreasing it. Output impedance decrease, similarly considering that fact. And the examples of this voltage series feedback amplifier is emitter follower. For voltage series shunt amplifier is a common emitter amplifier with a resistor RB connection between input terminal and output terminal. Current series feedback amplifier, common emitter amplifier with unbypass, and for current shunt cascade connection of a two-stage amplifiers. Now based on this analysis we have carried out, from this up to so far we seen that the input impedance, with the negative feedback, the gain of the system is reduced. Gain of the system is decreases, whereas we have the number of improved factors, number of advantage factors. One is the gain stability improves, bandwidth increases, distortion, nonlinear distortion decreases, noise decreases, input impedance decreases, input impedance increases, output impedance decreases. So we have the number of expressions. Based on that one we will have some examples. So let's firstly, if an amplifier has a bandwidth of 200 Hz and the voltage gain of 100, what will be the new bandwidth and the gain of if 5% negative feedback is introduced? That is the first question. What is the product of a gain and bandwidth before and after adding the negative feedback as a part in B? And what should be the amount of a feedback if the bandwidth is restricted to the 1 MHz? So these numericals, guys, you have to try it yourself and check it the answers with the provided the notes. Similarly, we have to go for the amplifier which has a minus 20 dB feedback introduced. What is the ratio of voltage gain before a feedback to the gain with the feedback? Determine the loop gain. If K is equal to 5%, then what is a gain before and after? So for you can also refer this one. So this number of numericals you can try. Now next we will consider amplifier with a 1 kilo ohm input impedance, input resistance, and the 50 kilo ohm output impedance as voltage gain of 40. The amplifier is now modified to provide the negative voltage feedback in series with the input. Calculate AVF, RIF, and ROF. For voltage series negative feedback, AVF is given as AV divided by 1. AVF is equal to AV divided by 1 plus KAV. Input impedance is given as RIF is equal to Rin into 1 plus KAV, and the output impedance with feedback is given as ROF is equal to RO divided by 1 plus KAV. So simply plug these values and find out its values. Now next, if the high input and the output impedance is the mean stability or the the gain stability are the main requirement of an amplifier, suggest the type. So we want that high input impedance and the high output impedance. So the higher stability is achieved by negative feedback. So definitely negative feedback. From this one, which type of a feedback we need to use it, whether voltage series, voltage shunt, current series, current shunt, or combination of voltage is higher. The high output impedance is achieved by negative feedback with a current gain driven. So the high input impedance is a result from the series feedback. So the finally current series feedback is a possible answer.